Hello, I'm Dr. Milan. I will be presenting our paper in which we predicted the optimal supplemental heat for piglets. The motivation for this research is based on the fact that newborn piglets need a supplemental heat source. They need this source because the thermal environment they live in, the foreign facilities, is usually controlled at the thermal comfort zone of souls. The thermal comfort zone of souls is situated between 10 to 20 degrees Celsius, lower than the thermal comfort zone of piglets. This creates a huge challenge for these animals because their thermoregulatory system is still under development. To cope with this, farmers usually provide a supplemental heat, and the intensity of the supplemental heat has huge impacts on these animals. If the intensity of this source is too low, piglets might die of hypothermia. On the other hand, if it is too high, they might run away from the supplemental heat source and get crushed by the sun. Hence, the importance of finding a balance between these two extremes. Our hypothesis was that this optimum balance, which we are going to call the optimal supplemental heat source, can be obtained with a bioenergetic balance model. We have the option of two bioenergetic models, the mechanistic models, which have been classically used today, and the machine learning models, which have been recently introduced in the field. The advantages of the mechanistic models are that they are based on fundamentals of engineering, in which they are easily interpretable. For instance, here, this is the prediction of the temperature profile of a piglet, and we can see that as we move away from the core, this temperature profile decreases going up to the skin surface temperature. These models can also generalize well outside of the range of data, in which we can ask and answer what-if questions. For example, what would happen if we increase the intensity of the supplemental heat source? And we see here that if we increase the intensity of the supplemental heat source, this temperature profile increases throughout. Well, the disadvantage of these models is at first they have several tuning parameters. For example, we have to define what is the thickness of this layer and what are its thermal parameters. We call all of those parameters a set of system parameters. Given a set of system parameters, the mechanistic models provide a point-wise prediction without any measure of uncertainty. On the other hand, the machine learning models they have a higher degree of flexibility, and because of that they have the advantage of removing subjectivities. For instance, in this model where we were predicting the respiration rate of piglets given environmental conditions, using machine learning models we are able to remove the subjectivity of defining the data relationships. If the relationship between respiration rate and environmental conditions should be linear, nonlinear, and what form of this nonlinear relationship. We simply define that there was a relationship between both of them, and the machine learning model automatically found that this relationship is basically constant, and after a threshold it increases dramatically, which matches with what other researchers have found experimentally. It also has the advantage of automatically selecting the predictors and what is the relationship between them. For example, we don't need to define that there is a relationship between air temperature and relative humidity and what is this relationship. Machine learning algorithm can automatically find relationships that are supported by the data. Because of this higher degree of flexibility, these models usually provide a higher accuracy and a measure of uncertainty, as we can see here in these two dashed brown lines. Well, the disadvantages of having this higher degree of flexibility are that the model can also learn counterintuitive functions. For example, over here, we have a machine learning model developed to predict the haircut surface temperature given the supplemental heat source. We see that for a deep learning model, as the supplemental heat source increases, the deep learning predicts that the haircut surface temperature decreases, which violates first principles, specifically the principle of energy conservation and what other researchers have found experimentally. Because of that, these models might not generalize well outside the range of the data and can be difficult to interpret. Hence, our goal is to first, we want to predict this optimum supplemental heat for piglets. We want to predict this optimum supplemental heat using integrated models that can combine the advantages of both mechanistic models and machine learning models, in which these models have to be based on fundamentals, they have to be interpretable, and they have to generalize well. In addition, they have to remove subjectivities of researchers in defining the tuning parameters, provide a higher level of accuracy, and a measure of uncertainty. After developing this model, we want to validate its prediction using experimental data. To go about with that, we collected data and gathered data from the literature. With this data, we went to the modeling phase. Here we are going to have above this dashed line the inputs of the model. Between these two dashed lines, the mathematical models themselves. Below this dashed line, we are going to have the outputs. We started with a mechanistic model that integrates analytical and numerical modeling, and it's represented over here. The mechanistic model needs boundary conditions and a set of system parameters to provide predictions. The boundary conditions were predicted using machine learning models represented over here. Given a few parameters of the farming facility, the machine learning models can predict several boundary condition values for the mechanistic model. The set of system parameters was obtained using Monte Carlo optimization method, which is represented over here. Given the distributions of system parameters which we obtain from collected data and data from the literature, the Monte Carlo optimization method samples a set of these parameters, which we are going to call set I of system parameters, and this is the input of the mechanistic model, which can now provide predictions of the haircut surface temperature, the skin surface temperature, and the skin surface heat flux using the sampled set I. We perform this sampling using the Monte Carlo optimization method 10,000 different times. So we have 10,000 different predictions for each one of these variables. We combine all of these variables using a simple learning algorithm so that we can further reduce the prediction error while providing a measure of uncertainty. So these 10,000 different predictions were the input for this ensemble learning algorithm, which combine all of those in what we call an ensemble. And the predictions from the ensemble are the final predictions for the haircut and skin surface temperatures and the skin surface heat flux. Now we performed an energy conservation balance. For this energy conservation balance, we needed an equation to predict the total heat production of the animal, the amount of heat exchanged through latent waste, and the amount of heat exchanged through sensible waste. The total heat production needs the weight of the animal, the surface area of the animal, and an equivalent air temperature parameter. The weight of the animal came from the experimental data, the surface area came from the surface area equation, which has as an input the weight of the animal. The equivalent air temperature parameter came from the ensemble itself. Now we can provide a bootstrapping for the energy balance. Basically, we are sampling each one of these energetic parameters 10,000 times for each single prediction of the optimum supplemental heat. So we have 10,000 samples from the THP, 10,000 samples from EL, and 10,000 samples from ES for each single prediction of the optimum supplemental heat, so that we have a non-parametric distribution of each of the optimum supplemental heat, and from that distribution we can obtain the expected value and its lower and upper 95% confidence intervals. So for the results of the model, we can start with the model to predict the surface temperatures. We have T, which represents a traditional set of system parameters, which are the set of system parameters that would be chosen by a highly trained and experienced researcher. M represents that we are using the measure values for the boundary condition. Compared with the model that had the boundary conditions predicted by the machine learning model, we see that there is not a huge difference in the error. If we compare that with the Monte Carlo optimization method, we see that the error was reduced by about 3.2 times. For the ensemble learning algorithm, we tested several different algorithms. The best one was the GP, which provided a measure of uncertainty and a further 5% reduction in the prediction error. For the ensemble predictions, its accuracy we can see here. For most of the time, for the skin surface temperature and the haircut surface temperatures, the predicted value matched nicely with the measured confidence intervals, and the prediction errors were between 2 and 3%. I want to highlight the fact that the prediction errors are really close to the measurement errors themselves, and that this is the second most accurate bioenergetic prediction. The first one being the one we developed using machine learning algorithms, which has the drawbacks we discussed previously. We performed a generalization and interpretability test for the predicted surface temperatures. In this and in the further figures, this dashed rectangle over here represents the range of the training data. We have that as the supplemental heat increases or as the air temperature increases, the mean haircut surface temperature also increases, which matches what we would expect. We saw similar trends for the skin surface temperature and their lower 95% and upper 95% confidence intervals. To validate our energy conservation modeling approach, we get the data from this John List time regulation obtained with previous research with the one obtained using our model. And we see that for most of the data points, our predicted value was really close to what other researchers have found. Finally, for the optimum supplemental heat, we see that as the weight of the animal increases or as the air temperature increases, the expected optimum supplemental heat decreases. We saw similar trends for the lower and upper 95% confidence intervals. This result tells us that if we control this supplemental heat source dynamically, we can then ensure thermal comfort while reducing energy consumption of the farming facilities. For instance, if we look at the range between 15 and 19 degrees Celsius, we see that compared with the required optimal supplemental heat at the beginning of the farming cycle, at the end of the farming cycle, we have a reduction of about 200 watts. In conclusion, the integrated model performed well. It was 3.2 times more accurate than the mechanistic model itself. It provided a measure of certainty, generalized well outside the range of the training data. It was easily interpretable. Its error were between 2 and 3%, and its John List time regulation agreed well with published data. This dynamic optimal supplemental heat has the potential of increasing energy efficiency in the farming facilities through controlling this energetic requirement. Well, thank you for watching this video, and if you have questions, please feel free to email me.